traditional time series models that get used in lots of applied settings. So the motivation for my research is basically macroeconomic forecasting. And this is something that I worked with a little bit. I used to work at the Federal Reserve before I came to school here, and so this is something that became important to me and has been actually very important in the last couple of years. So in macroeconomic forecasting and in finance, there's basically a lot of standard models that get used. There are kinds of ARIMA models, GARCH models, AR, moving average models, the standard kinds of time series things. Another sort of model that gets used are dynamic factor models, which is what I have a picture of there. So this is, you observe some time series and try to infer some latent factor from it. In this case, this is the probability of being in a recession. So you want to know if you're in a recession or not in a recession, and maybe this changes the mean of macroeconomic variables that you observe, like GDP or unemployment or something like that. There's also a lot of systems of equations modeling that get used, especially at central banks. In this case, they have sort of, maybe hundreds or thousands of different equations that display various interactions between macroeconomic time series, and then they want to learn a whole slew of parameters and try to use that to make predictions. And then the fourth variety is called dynamic stochastic general equilibrium models. And this basically, I'll get into this a little bit later, but this is kind of the standard macroeconomic model that has really come about in the last 30 years. So here's some data, and this is very particular data set. Basically, these are income, consumption, investment, and hours worked. So this is the U.S. since 1948, and this data arrives quarterly. So basically, there's about 250 data points for each one of these time series. There's, of course, lots of other time series that you could use, and so you might want to predict, you might want to have hundreds of time series with the number of observations of each of those time series being actually very small, so something on the order of 250. And this data has been detrended and made stationary using a couple of techniques that are sort of common. So this dynamic stochastic general equilibrium model is going to sort of be my straw man. It's the guy that gets used an awful lot, and in some sense, I think it doesn't work very well. And the reason that you might imagine it doesn't work very well is, as I explain it, you'll see. So basically what happens is you imagine that there's one agent in the economy. So I'm going to have one person, and that's my stick figure, and he represents the entire economy of the US. So every individual in the United States, all 300 and whatever, some million of us. And basically he makes optimal decisions that determine how much he's going to work and how much he's going to sit around on his butt and do nothing. And he does this by maximizing a utility function that tells him how much enjoyment he gets from the things that he can buy with the money that he makes from working. And he can only buy one good. So he buys one thing. And if he doesn't work, then he's sitting around. So he's going to basically maximize this in expected value, and there's going to be some constraints, that say there's 24 hours in the day, so you either work or you're sitting around, and some other things. And then when I do that, that gives me a model for the entire economy. Okay. So the form of this model, this actually arose in about 1976, and there was a very famous critique which actually came out of Carnegie Mellon from the Tepper School, and it said that the sorts of models that we use in economics now don't work for forecasting, because if I'm a central banker and I make forecasts out of this model and then I make a decision based on the forecast, well, that changes all the parameters in the model, so my forecast is going to be complete garbage. Okay? So I need something that is somewhat separate from the sorts of decisions that I make that's based on fundamentals. And the fundamentals for an economist are utility maximization and the desire to, for every person to behave in such a way that they're the happiest that they could be. And so these models are basically an attempt to incorporate that into time series forecasting. And if you want to hear a little bit more, I can maybe go into talk about it a little bit at the end. So basically, here's our data again. And what happened in economics is sort of a standard thing that you might imagine. Basically, in sample, if I look at how this model performs in terms of forecasting these time series, it behaves really well. But then if I try to forecast an outlier, say like the recession of the last 3 years, it behaves really poorly. This model and basically all other economic forecasting models were very much unable to forecast the recession of the last 3 years. And so they really took a lot of flack from government officials. There were actually hearings in Congress that said, why didn't you forecast this recession? Explain to me why your models are so bad. And DSGE models couldn't do it. Other models couldn't do it either. And the solution in the economics literature was, well, this model has like one guy in it. Maybe we should add some more things and make it a little bit more natural. Maybe we should incorporate things like the financial sector, which is not in the model to begin with. So, that was the main cause of the recession. We might want to add the financial sector back in. We might want to, make the model more realistic to what we actually think the economy might be. And so we're going to add more things. We're going to add more parameters, more latent variables, lots of other stuff to estimate. At the same time, there's no more data now than there was before. So the question is, how is this going to help? Is this going to help or hurt prediction error in the future? So you know that from 701 or 702 or something like this, adding more stuff to the model is going to lower your in-sample error. Right? Your training error is guaranteed to go down as you incorporate more things. But it's a little bit of a question as to whether or not out-of-sample error will go down or will go up. Because you want to be able to trade off the complexity in your model with the amount of data that you have. And so, there's lots of standard ways of doing this, like AIC, BIC, Bayes factors, those kind of things. And these are used to some extent in the literature, but what I'm going to do is use some machine learning techniques. So the big picture for this research is your favorite model often does worse out of sample than in sample. And you want to know how much worse it's going to do. And the sort of technology for doing this are to use quantitative risk bounds. Now, in the literature in computer science, this technology is usually for IID data and for the kinds of computer science models you're all familiar with, like support vector machines or kernel regularized methods or things like that. And so what I wanted to do was apply these methods to time series data and standard models. And so the things that you need in order to be able to do this are to determine how much information you really have in the data, how much different is your dependent data from independent data, and then to say how flexible is your model. And so this is going to, in some sense, allow you to assess your model in a rational, maybe objective way. So what exactly are risk bound and why might I want to use it? Well, your favorite model fits the data well, and you'd like to know with some confidence how well it's going to fit in the future. So I'm going to define the risk here as a function f that I take for forecasting y from x and some loss function L, and I just want to take the expectation with respect to some underlying data source P that I don't know. So why might I care about the risk? Well, it sort of tells me how well my model is going to do on average. What's the average cost of making bad predictions with this model. And so it gives me a natural way to compare to other models. The problem is, I can generally not find that risk in closed form. I don't know P, and so I'm sort of hopeless. If the model was well specified, maybe I could simulate something out of the model, but the model is never well specified, so I need to find something else that can tell me what I can do. So a question that I get kind of a lot, especially if I give this talk to an economist, is, well, I don't really care about predictions. I want to make inferences. I want to learn parameters. And so the sort of steps that they go through is, you need that the structure of your model is at least approximately right if you want to believe any of the estimates that you have for parameters. And so the standard justification is, well, our model fits really well to the data. The fit is so compelling that I'd have to be crazy to think I didn't sort of get the structure right. And therefore, for that reason, when you come to me with your estimates of parameters, I should believe them because the model fits the data so well. And so this is kind of about not fooling yourself when you say that the model fits the data. So you want to make sure that I can actually believe that your model is fitting the data well if you want to present to me inferences. So of course, statistical learning theory, it's basically been around since the 70s, and especially since the 1990s, we've sort of figured out how to get confidence intervals for the risk. And these confidence intervals are nice because they hold uniformly over all p. So despite the fact that you don't know it, the confidence interval will hold uniformly. It's distribution free. It's also agnostic. It doesn't assume that your model class is well specified. So I can use this regardless of the quality of my model class. And they're also non-asymptotic, and it holds at finite n, which is really important to me because in economics and in lots of other cases, you don't have asymptotic data. You have a finite amount of data, and you want to know if your model is going to do well or not. And so, of course, this has been good for machine learning. It basically has made machine learning into what it is today, which is a major industrial technology. So sort of the plan of the talk, I'm going to do a quick review of learning theory in the IID setting. And then I'll talk about how do you introduce dependence into this IID setting. Then I'll talk about the particular measure of model flexibility, model capacity that I'm going to use. There's lots of them, but present our result and talk about some extensions and other considerations. So the basic form of statistical learning theory looks something like this. You get IID data, pairs, x's and y's, and you want to use some class of functions, script f, to predict y from x. Okay? And the standard thing that you might look at is the empirical risk of some fixed function. So you pick an f out of that model without looking at your data, and you say, what's the average loss of this particular forecasting function on the data that I've observed? Now, if that function being fixed, then the average, the sample average, is close to its mean. And in particular, in this case, it's equal to the mean, the risk that I'm interested in, plus some mean zero idiosyncratic noise variable. And using this fixed function, I can get nice concentration inequalities for how far the average is from the mean. And these are usually exponential, where the parameter and the exponent depends on some constant having to do with the model class, the amount of data you have, and the confidence that you want, how close you want the average to be to the true risk. So that's fine, but what about when I want to choose functions from the data? So the sort of standard way is maybe I'll pick a function out of my model class that minimizes the training error. And of course, this amounts to minimizing both the true risk that I want to actually minimize and the idiosyncratic noise. So that creates a little bit of a problem. So I can get similar concentration inequalities if I have finite numbers of functions in my function class. So if I assume that f is finite and that for each f in that function class I have that sort of concentration inequality, then I can just apply a union bound and I can say, well, for the worst function in the function class, my average is close to the mean. So what if it's not finite, which of course it never is? Then what you need to do is have sort of talk about the number of effectively distinct functions in your function class. And if this is small, you can still get similar results. So you can even allow the size of your function class to grow slowly with the amount of data that you have. So I'm going to call this number g, and it depends on the amount of data I have in the function class. And so you can still get that sort of same concentration inequality where I've just replaced the number of functions in my function class with this growth function. And then I can trade off precision, how close my average is to the mean, which depends on epsilon, and confidence, which is going to depend on n and epsilon, and that's the right-hand side of the inequality. And what you can do to this probability inequality is invert it to get some sort of confidence bound. So basically I can say I can demand probability at least 1 minus eta, and then I can say that the true risk of the function that I've chosen is less than the empirical risk plus some penalty, which depends on, again, that growth function and the amount of confidence that I have. So if you're interested in asymptotics, what does this kind of result give you? Basically, it gives you a uniform law of large numbers. It says for every function in your function class, the training error is going to converge to the true risk and probability. It gives you risk consistency. It says if I'm interested in the optimal risk, which is of my model class, then the training error of the function that I select is going to eventually achieve the optimal risk. So what were the things that we needed to make this work? Well, first we needed that pointwise deviation inequality, a sort of finite sample law of large numbers to hold for every function in my function class. And second, we needed a way of saying how big that function class is. And so both of these results are extensively developed for IID data and computer science models. But I want to handle dependent data and standard time series models. So that's what I'm going to cover next. So the first thing that you want to do is, how do I get dependent law of large numbers from independent law of large numbers? And the key assumption that I'm going to make is that the data I observe comes from a stationary beta mixing distribution. And what that means, basically a beta mixing coefficient is the total variation distance between joint distribution of an infinite dimensional joint distribution that has some gap in the middle and the marginals of that distribution. So here I'm looking at from time minus infinity to 0 and from a to infinity, and I look at the joint distribution of those two time sets, and then I look at the marginals and I see what the total variation distance is between those two. So it's basically saying, how far am I from independence? In the intuition, basically, a process is said to be beta mixing if these coefficients go to 0 as the separation increases. So at large separations, events are nearly independent. That's what the assumption means. So what can you do if you assume this? Well, basically, if I have a time series y1 to yn, I can divide this time series up into blocks. And so in this case, I'm going to divide it into 2 mu blocks, each of length a. So now if I take every other block, then every other block is separated by length a. And so I know that the dependence between, in this case, the blue blocks is less than or equal to beta a. And so what you can do with this is then approximate probabilities of events over the dependent blocks with probabilities over the IID blocks. And so by a nice theorem from Bin Yu in the early 90s, the difference between these probabilities is less than or equal to beta a times the number of blocks mu. Okay? So the intuition for this is that if I have n mixing samples, this is really like I've had mu, where mu is less than n independent samples. And then I can use IID laws with small corrections. So where might you get these mixing coefficients? Well, in this talk, I'm going to assume that they're given to you. Many time series models are known to be beta mixing. And in fact, you can find the beta mixing coefficients if you know the true model. So ARMA models, Gaussian state space models, Kalman filter kind of things, they're all known to be beta mixing. Any Markov model or hidden Markov model is known to be beta mixing. And you could get the actual coefficients if you knew the true parameters of that model. My advisors and I actually derived a non-parametric estimator based on adaptive histograms for how to estimate mixing coefficients from a sample of data. And it's probably not an optimal estimator, but it's the first one that exists. And if you were to basically use an estimated version as opposed to the real version, this is going to sort of complicate the formulas that I'll give, but it's not going to change the basic idea. So the next thing that you want to do is measure that model complexity. And there's lots of ways of doing this. There's a huge literature on all of these different ways. So the sort of standards are algorithmic stability, discrepancy, if you look at covering numbers of a function class or packing numbers, something like that. The most common ones in the literature are Rademacher complexity and VC dimension. And basically, Rademacher complexity says how well does my model fit IID plus 1 minus 1 random variables. And there's some good benefits to using Rademacher complexity. First, it gives the tightest risk bounds. And you don't actually have to use theory to calculate it. So if given a sample, you can do some estimation tricks, and you can get an empirical Rademacher complexity, which is very useful. The problem is that it requires bounded loss functions. Now, in a lot of machine learning applications, you work with classification, and so an assumption of bounded loss makes perfect sense. In time series, most of the time you're working with regression problem, and you use something like squared error loss, and it doesn't actually make a lot of sense to assume a bound. And in fact, if you go through and calculate risk bounds using Rademacher complexity version, you'll find that the bound depends extremely strongly on the upper limit that you've chosen. In fact, it depends on that upper limit in such a way that the bound is mostly useless because it's completely driven by the upper limit that you choose. So what I'm going to work with is VC dimension, which is basically the worst case growth rate in the covering number. But all of these things are related, and you can sort of get from one to another. So why might I use VC dimension? Well, first, it's fundamental in some sense. So it was shown by Adams and Nobel that finite VC dimension is necessary and sufficient for learning function class from ergodic sources. It leads to distribution-free bounds, which may be more conservative than other versions, so probably more conservative than an equivalent Rademacher complexity, but still. It's very nice because this actually will work with unbounded loss functions, whereas Rademacher complexity won't. The big negative of VC dimension is that it's very difficult to find theoretically, and it usually involves doing a lot of combinatorics and is sometimes just impossible. We actually show how to measure it accurately via simulation. So basically, if you can simulate data on your computer, you can fit your model to that simulated data in a certain way, and the result will be that you can use the estimated VC dimension and plug it into the resulting bounds with a little bit of a correction. So I'll sort of quickly define VC dimension. This comes, of course, from the idea of shattering. So a collection of set C shatters some finite set S when I can pick out all the subsets of S. Okay, and if I let S be, this is sort of the standard example. If I let S be a set of points in R2 and C be the collection of half spaces, then I can shatter some 3-element sets. This is a particular 3-element set that I can shatter, but I can shatter no 4-element set. So the shattering number of this particular set is 3. Then the VC dimension is just the size of the largest set that some class can shatter. The VC dimension of indicator functions is just the VC dimension of the corresponding sets. And in my case, I'm interested in real valued functions. And the VC dimension of a class of real valued functions is just the VC dimension of the collection of level sets. So before I mentioned the growth function, and a growth function of some collection of sets is just the number of distinguishable functions with n observations. And this, of course, grows like 2 to the n, so it's not very useful. But for finite VC dimension, you can show that the growth function is bounded by something that's polynomial in n. So this gives you the name dimension, basically. So 2 quick examples. For p-dimensional linear models with an intercept, the VC dimension is p plus 1. In general, the VC dimension is not equal to the number of degrees of freedom. Here's class of sine function with 1 parameter, but the VC dimension is infinity because basically you can make the sine function wiggle as quickly as you want, and you'll pick out every point. So those are the sort of background. Now, how do I do this for time series? So this is different from the IID case. Basically, I'm going to observe one time series that may live in whatever space I want it to observe in, but I'm going to observe n data points. And then I have to deal with whether my predictor is fixed or growing memory. So in sort of the standard IID setting, basically you have x's and they're of a particular dimension. In this case, I might use the most recent past, or I might use all of the past to make forecasts of the future. And so something like an AR model depends only on the most recent D observations. But moving average models, state space models, those depend on the entire past that you've observed. So you have to be a little bit careful with how you define empirical risk in these cases. And so these are my 2 different definitions. The first one with the hat is for fixed memory models, and the second one is for growing memory models. And I'm going to have results for both cases. But even so, generalization error is the same. I want to look at, given n data points, what's the expected loss of predicting n plus first data point. So some assumptions are necessary. The sort of additive bound that I showed at the beginning relies on bounded losses. but I'm going to use unlimited losses, and these have multiplicative bounds rather than additive bounds. The key assumption is going to be that basically the qth normalized moment is going to be bounded. So this is weaker than the usual distributional assumptions on noise. Bounded loss immediately satisfies this. Anything that's sub-Gaussian satisfies this. Basically anything that you can get a moment on will satisfy this. So obviously, if the loss is Cauchy distributed, I'm hosed. So this is Vapnik's IID result, which says that I have some nasty function of the qth moment, where q is the number of moments that I had. But basically, the normalized risk is going to be close to the empirical risk, and I still get a sort of exponential decay with some stuff that depends on the moments, and 4 times the growth function in front. So this is Vapnik's result from the early 90s. So now I can put all these pieces together to get results that I want. So I'm going to use the IID result that I just presented to bound the deviation for each function f. I'm going to use mixing to find out how much information is actually in the data. I'll use VC dimension to measure the capacity of the model, and the result are going to be generalization error bounds, possibly including a correction for growing memory. So this is the main theorem. If I assume mixing moment bound, that f has some fixed memory length d, and that the VC dimension is known, then basically I choose integers mu and a and some epsilon between 0 and 1, and I get this exponential concentration inequality. And the difference between this one and the one that I just showed you from Vapnik is that there's a factor of 2 in front, and that there's this additive term that depends on the mixing coefficient. Also, rather than n data points, I now have mu data points. So the meaning is that with high probability, all predictors in my function class come sort of within epsilon of their true performance after this much data. And therefore, with high probability, that function that I choose will do no worse than this. So just a sort of picture, if I have the amount of data is on the x-axis and the confidence that I want is on the y-axis. So if I want if I demand really, really high confidence, the training error and the true risk are very close together, and I have very little data, then I get a trivial bound, right? The probability is going to be less than 1, which tells me nothing. Of course, if I go out to having a lot of data and allowing them to differ in some way, then I can get really good concentration. That probability shrinks very quickly. So just for a little bit more intuition, you can invert this thing by demanding confidence and finding precision. So what I have is if I choose eta in a particular way, then with probability at least 1 minus eta, I get that the true risk that I'm interested in is less than or equal to the training error times a multiplicative factor, which is larger than 1. And it depends mainly on this function down here, capital E of f. And that's how this works. So here's a similar picture. Again, for small amounts of data and really high confidence, I'm going to get that multiplicative factor is going to be infinite. And as the amount of data increases, I'll get to the place where the factor will be close to 1. And my training error will be very close to the true risk. So what sorts of extensions can you do with this? Well, if I don't know or can't find VC dimension, then I can measure it. I can add a little bit of a fudge factor to the measured dimension, plug it in, and add a little bit more probability of error. Given arbitrary simulation time on your computer, the impact of measurement will go away. If I have a growing memory model, I need to make an assumption on the class F. I need to assume that it's linear in the data. Now, most time series models are linear in the data. For instance, state space models look like weighted averages of previous observations. And so in these cases, I can use a finite memory approximation, apply the finite memory theorem, and add a little bit of an extra penalty, which shrinks as the order of the approximation grows. Something that comes up a lot is what about priors or regularization? It's fine if you are interested in linear models, but what about penalized linear models, perhaps, or some sort of Bayesian perspective? Obviously, this whole thing is a frequentist approach in general. So if I'm a subjective Bayesian, this doesn't make a whole lot of sense. But I can build regularization or prior knowledge into the model class F. And in that case, you can just measure the VC dimension and use the proper one that you're interested in. Can also use this for model selection. So if I have multiple models that have different capacities and different minimizers, typical model selection criteria like AIC or BIC says choose the complexity that gives you the smallest training error plus some penalty that depends on complexity. And the problem is that all of these work sort of asymptotically at best. AIC assumes that you're in the limit and you have a basic nearly normal likelihood function and things like that. Instead, you can use structural risk minimization, which is to use the bound that I showed. And this has nice properties, which Vapnik and Massart have proven, that basically say that this will pick out the best predicting model with high probability. It's risk consistent in infinite dimensional problems. And so it's something that gives you confidence even in finite sample. So here's a little worked example. And this is not the greatest, but what you have here is daily log volatility for IBM stock since 1962. And so the sort of standard model that you would use for this is a stochastic volatility model or a Garch 1-1, something like that. And there's a huge benefit to having a model that can predict really well, because if you can predict slightly better than somebody else's model, you can make a whole lot of money. Right? So in this case, you see that the stochastic volatility actually does a little bit better than the mean, though not a whole lot. So we're at like 5%, right? There's about a 5% improvement for using the stochastic volatility model relative to just predicting with the mean of this data. At the same time, if I use AIC to do model selection, it says very strongly that I should be using the stochastic volatility model. If I use instead my risk bound, it says you should probably be predicting with the mean, because basically you're just not getting enough improvement out of the stochastic volatility model to actually believe that in the future it's going to perform well, even though it's performed well in the observed data. And the VC dimension for these three models is just over here. Stochastic volatility model is a growing memory model, so I had to use a finite memory approximation. And the VC dimension of the finite memory version is 3. So then that's the one that you need to plug in. So just to kind of recap, what I needed to do was I assumed stationary mixing data in a moment bound. Then I can use mixing to say how much information we have in the data. Measure VC dimension, or use it known if I have it, to find the capacity of the model. And together, I can bound how optimistic the training error is as an estimate of risk. The bound holds for finite n, which is what I wanted in the first place. It holds for misspecified models, and it holds for all data sources. So what are some things that you can do with this? Well, the first thing that you would want is probably a more direct treatment of the infinite memory case. But I had to assume that the model is linear in the data. There's other things that you could do that are much more complicated than that. And it would be nice to have a more direct way of doing that. The beta mixing assumption is a little strange. It's not something that you often see. You might imagine looking at autocorrelation or something like that. So it'd be great to have another way of measuring dependence that makes a little bit more intuitive sense to in a standard way. There's other notions of model capacity that I mentioned besides VC dimension, especially Rademacher complexity. And we looked at doing Rademacher complexity, and there's actually a way that you can get this to work without using strong mixing, so without the beta mixing assumption and using Rademacher complexity. But it's it requires a lot of other assumptions. Another great thing to do would be to have sort of sharper data-dependent risk bounds. Basically, if I could do stationary bootstrap or something like that, and bootstrap a future time series, see how well my model predicts in the future. But in order to do that, you need some sort of coverage guarantee for a stationary bootstrap. So you need a lot of conditions as to the smoothness of your the model that you're using and the loss function, things like that. But that might work very well, actually. This extends easily to panel data. So if I have maybe dependent x's and y's that are observed off of them, I can use this all of the framework that I've developed here. And then sort of one of the more relevant things probably to machine learning is that you can bound regret rather than risk. So I argued that I was interested in risk, but if I look instead at a backward-looking measure of the performance of my model, if I say, you know, I had a whole lot of models that I could have chosen, and now when I observe the data, I look at how well each of them did, and I experience some loss that's related to not using the best predicting model. That gives you a lot of power in terms of talking about regret in a time series or even adversarial case. So basically, in summary, if I want to bound generalization error, this is a sound and objective way to evaluate misspecified predictive models. We established how to do it for time series data and time series models. The bounds shrink as you get more data, and they grow as models become more flexible or as dependence increases. And then if you want to use it, all you have to do is run the calculations, and you can just plug everything in. There's lots of ways to extend this and lots of ways to apply it. So thanks.
So all of these risks are about making a specific prediction some amount of time into the future, correct?
That's right.
And so do you have results that say how you chain these together if you're interested in making a prediction? Like, what's the risk of using my model, you know, farther in the future if I chain my predictions together?
So if you're interested in just like one, you know, suppose instead of predicting 1 step ahead, I was interested in predicting 10 steps ahead, then I could just define risk in exactly the same way and look at the appropriate training error. If I'm interested in predicting all of them at once, like time 1 to time whatever, t plus x, I don't have a result that would say how to do that. I think that's an interesting idea. I don't think it would be that difficult. But
so there's a practical question as well, because the model selection criterion would presumably depend on what you decided you were trying to predict.
Right. Yeah, for sure. I think that to some extent you could, I mean, I want to be able to do vector-valued predictions. So in some sense, you could imagine predicting multiple steps ahead at the same time as just a vector-valued version.
Right.
I think, yeah, eventually the model selection is going to be a little bit more difficult, but the bound should work, yeah.
The IBM volatility example was really nice. Have you tried this with the sorts of things that central banks are predicting every day? How
Sure.
far off are their GDP estimates?
Yeah, so the problem with that is there's basically no data.
Okay.
So the actual length of the data set is about 250 data points. When you look at the mixing, you end up with about 20 data points. So now I want to do basically predictions with 20 data points, and you're out of luck. There's all sorts of there's constants in there. The VC dimension is something larger than 1, so you're out of luck, basically, which is sad. But it basically says.
How many data points do you need before you start?
So I mean, on the order of 1,000, yeah.
1,000.
Yeah, like 1,000, yeah.
You're assuming IID, like the points are IID, right?
No, so the data that you observe is dependent. And so what you need to do is convert, that's what the mixing assumption is doing. You need to convert from these dependent data to something that looks sort of IID. So in that example,
your analysis is IID, but you're not making.
That's right. So it's how do you convert a dependent setting into an IID setting where you can use sort of standard results that you understand. Yeah.
Do we know how tight your bounds are?
That's a good question. Probably not very tight. So there's a couple ways that you lose the tightness. One is using VC dimension. I mean, that in itself hurts you a lot, but there aren't any other ways, as far as I know, for unbounded losses. So you're not going to, you know well that in a Rademacher sense, you can basically get rid of the amount of parameters that are in there. So I'm always going to have the VC dimension in there. So I lose that tightness from that. The other way that it's not tight is the beta mixing way of moving from dependence to independence is a very loose bound on that probability that you need. So I've looked a lot at how do I, what other way of doing this can I do that would be a little tighter, but it's been really hard so far. But yes, so it's not that tight for that reason mainly.
So when you're doing model selection, the lack of tightness at the bound is going to cause you to be extremely conservative in the complexity of the model
Yes.
that you'll accept. So in the IBM example,
Yes.
do you have a sense of whether, if your bound were just a bit tighter, the central banks could be right as opposed to wrong?
That's a good question. Like, how much tighter would the bound need to be before I could? Well, I mean, I guess I could.
I mean, a factor of 3 tighter or something.
Yeah. So a factor. Yeah. Exactly. Basically, a factor of 3 tighter.
Which seems plausible, right? That it could
Yeah.
be
So
a factor.
so maybe. So I guess a good way to look at this would be how much would I need to change mu so that I would then use the stochastic volatility instead of the mean. So how much closer to independence do I need to go to get something that would be plausible for actually using the stochastic volatility model? Yeah.
Right. Yeah. So that and the looseness due to the VC, right? So there's 2 sources of looseness.
Right.
Yeah.
Right.
Cool.
Right.
You know that cap A, when you trying to learn the data mixing, but here it's only, do we have any intuition in real data how much that A is usually is it about 7 bits?
Do I have a, so the so the way that you choose it, you actually can choose it yourself. So it's not that you need to, but the longer A is, the smaller beta is going to be. So if you look back here at the where is it? So if you look here, there's this 2 mu beta term. So as A gets smaller, mu gets bigger, which is what I want, right? But then this thing is linear, so I need the beta mixing coefficient to decrease fast enough that it'll kill that out.
Mostly from a data perspective, what is your intuition about, what was, when you learned that value, what was it usually?
I'm not sure what you mean usually. So when I do it, I would choose a bunch of different mu's and A combinations, and I would pick the one that gives me the best result.
I think she means what is in general data, how long does it take to mix or whatever? Like, what is this beta mixing coefficient for time series that you've come across?
Right, so if you look at, let's see, so if you look at, for instance, a Markov model, I guess I can show you. So if you look at Markov processes, then beta A looks like rho for some rho to the negative A. So that basically gives you an idea of how quickly it'll go. So you can get exponential bounds if you have Markov models. So then, yeah. So does that sort of answer your question to some extent? Yeah. So if your dependence is somewhat nice, then it goes really fast. But if it's not, it doesn't.
I have a really silly question. So usually when you think of VC dimensions, I think of it for classification.
Yeah.
And then when you're doing it with real valued functions, you mean for the level sets?
Yes.
So you mean VC dimension of the level sets of it?
Yes. Yeah. So yeah. Is that
Yeah.
okay? I mean, I can write it down, but.
No, I think I know what the definition is, but at least that's how, Larry, when he teaches it, will say VC dimensions is usually for classification problems, and then you have covering numbers and all that stuff.
Right. So if you do, basically you look at the indicator of f of x minus, I don't know, some parameter c, and then it's the VC dimension of this thing combined. So it's the union of f and c.
Okay.
Yep.
Your results are worst case results.
Yes,
right? So
for
can you
sure.
go for, I don't know, average case?
That's a very good question. I don't know. I don't know the answer, but that's definitely a good question. Yeah. Danchi?
You mentioned earlier that you had an estimator for the beta mixing.
Mm-hmm.
Did you use that in the?
In the example that I showed, no, I didn't. Just because it's a pain.
Would that be a practical strategy?
Would it be practical to estimate beta and then plug it in?
And would that estimator have problems that would impact these risk benefits?
Yeah. So problems. It's going to make the bounds looser.
Yeah.
But
It tends to overestimate?
it does tend. In fact, it has to overestimate because you're estimating something. I'm looking at a total variation distance that I want to get close to 0. And so if I do the density estimates, basically they're always going to be slightly different. I'm never going to estimate exactly 0. So that's part of the problem with the beta mixing.
So would you suggest that to be a practical strategy as opposed to, I mean, I think you just kind of set them, right? You kind of set a beta mixing
Right.
amount.
Yes.
So is that
The idea is, yes, that you can estimate it and plug it in. Is it going to give you worse bounds? Yes. Yeah. Is it going to actually work? For large amounts of data, it'll be fine. For small amounts of data, it's not going to work at all. But
yeah, I mean, could you do it as some kind of tuning parameter then?
yeah, so that sort of in the same way that Jeff was asking. Basically, you could say, instead of dealing with the beta mixing coefficient at all, you could say, how much do I have to turn this down? How close do I have to make it to independence to get back what I actually want to get back? And so I think that's probably a really good way of looking at it.
Yeah, I guess, I mean, you could think of it that way, but there would still be some sort of, like, there still would be something in the data that would tell you that you could justifiably turn it
Yeah,
down.
for sure.
So,
Yeah.
so,
Yeah. Yeah.
I didn't really catch what you said, but your way of estimating the beta mixing is you're going to do a density estimate and then find what the total variation is 0. But isn't that
So
a very strange way to do this? Like you want one number, you're doing a density estimate and doing.
Yeah, it's a terrible way of doing it.
I mean,
But
to me it sounds like
I mean,
you want like
yeah, no, it's exactly right. Yeah. So
computer density estimate and calculate its variance.
yeah, so you do all sorts of mess to get at something, but there's really, as far as I can tell, no other way of doing it. I mean, it's one of those. I mean, so there's the definition. Like, so the first.
that's trying to estimate total variation.
Right, I'm trying to estimate total variation distance between densities. So it's kind of hard. It's kind of hard to. You can give bounds on it. That's right.
Bounds without estimating the densities.
That's right. Yeah.
So there's like these techniques for kernel mean map descriptors, right? Looking at the distance between, I don't know, I mean, you presumably lose something if you try to go between distance between two kernel mean map descriptors and total variation distance. I don't know how much you lose, but do you think that would be a practical?
Yeah, I think it might. So like Barnabosh has talked about, you do mutual information. Yeah. So there's information mixing you could do. I mean, if you could use information instead of beta mixing in the first place, then he has a very nice estimator for doing information mixing that I think would work really well. Another possibility is you can probably, you can do something with a copula and make this really nice so that if you could estimate the copula, then you could do it really easily.
That's a strategy for increasing just about any paper. Do something with a copula.
I'll keep that in mind.
Do you think you could use this blocking procedure to cross-validate or just show cross-validation?
Yeah, I think you could. I think you could probably do that. Yeah, because I mean, in general, cross-validation is really hard in time series because it doesn't make a lot of sense what you're removing. But I think once you move to this idea of IID blocks, then essentially you could just remove a block and try to predict that using the other blocks. I think that might work well. Though, actually what happens when you do this, the training error is still all of the data. You're not just calculating training error just on the blocks. The blocking is just sort of a way of figuring out what the appropriate N is going to be. So, Yeah, so I'm not exactly sure, but I think it may be something that would work. Yeah.
Thanks.
Thanks, guys.